everybody, how you doing? Thanks for joining me. This is the third part in our three-part series doing volt drop calculations. The first part we took a look at what the distance we could go with a certain size conductor was given a predetermined load. The second video was determining what size conductor would be required to feed a load given a certain distance away. In this video, it's going to be similar to the second video with slightly different results using that note 3 in table D3 and then seeing what the next smaller size conductor is and if we can use that. In the second video, we sized the conductor and then checked the next smallest size, and it turned out that the next smallest size was not sufficient to carry the load. We're going to check the same thing in this video. So we're going to start again with our 347 600 volt 3-phase 4-wire panel supplying our 51 amp load. And again, this is a 51 amp 600 volt load. And in this case, what we're going to do is locate this load 152 meters away from the panel. Okay, so again, what we're trying to do is determine what size conductor is required to supply this 51 amp load located 152 meters away from the panel. A couple more pieces of information that are important in the question. We have our RW90 XLPE unjacketed 600 volt conductor. We have 75-degree terminations at both our panel and our load. And then our obviously the insulation temperature is going to come into play when we go to check that distance correction factor on the next small size conductor. So let's get started with our calculation. Okay, so we're going to go back to our base formula, what D3 is essentially based off of. We know that if we were to calculate total distance would be equal to whatever our actual voltage is over 120, as D3 is based off 120 volts. Multiplied by the actual percentage divided by 1%. Again, table D3 is based off of a 1% volt drop total. And then multiplied by the distance correction factor. We're going to apply that distance correction factor later. So I'm going to just kind of strike that out of here for now. So this would be to determine the distance I can go with a certain conductor. So we kind of, again, have to transpose this formula. And in order to do that, what we're going to do, we're going to take our total distance, we're going to divide it by, again, actual voltage divided by 120, multiplied by actual percentage divided by 1%. Okay, and again, we're going with the allowable with a branch circuit, right? And again, the maximum allowable is a 3% volt drop. So, given those numbers, we're going to punch some of those variables in there. And what we're looking at is we have 152 meters divided by our actual voltage of 600 volts divided by 120 times the 3% allowable divided by 1%. If we run those numbers in there, it gives me 10.133 meters. Now, I know I'm supplying a 51 amp load, and I know that 10.133 meters is the distance that I'm going to look at. So at table D3, what we're going to do is cross-reference. We're going to check there is no 51 amp load. There's a 50, but it tells me very specifically that I'm going to go up in note 8 for currents intermediate to listed values, use the next higher current value. So we have to go up to the 63 amp column or row, and we're going to cross-reference that all the way across until we find something that can accommodate that 10.133 meters. And we end up at 12.5, which if we go all the way up to the top, tells me that that is indeed a number 3 AUG. Okay, so it's telling me that I can supply a 51 amp load located 152 meters away with a number 3 AUG. Now, we always want to try to go with the cheapest option possible and see if we can get away with a smaller size conductor. So again, that's what we're going to do in this example. We are going to check what the distance of a number 4 AUG is. Okay, so D3 under the 63 amp load, a number 4 AUG is capable of 9.9 meters. And I know that doesn't sound like it's long enough, but this is where we get to allow that distance correction factor from previous. Okay, so to calculate the distance correction factor, what we're going to do is we're going to go to note 3 at table D3. Okay, And that's based off insulation temperature. So I stressed the point in a previous video, we make sure that we are using the insulation temperature when we are going to the note 3 in table D3 there. But before we do that, before we find the one that we're looking at, we know that in the 90-degree column, again, what I'm going to do is kind of apply the largest distance correction factor first. Okay, and what that's going to do is tell me whether I should even bother applying the actual distance correction factor. Okay, so if I was to go 9.9 times 1.08, I run the numbers. This gives me a higher number than this, which means, yes, we probably should find what the actual distance correction factor is and apply it to my number 4, 9.9 meters. So to determine my distance correction factor, so DCF, we're going to do this. We're going to take the actual load and we're going to divide it by the allowable ampacity of the conductor in question. Okay, and in this case, the conductor in question is our number 4, right? So the actual load is 51 amps divided by the actual ampacity. And this is the part that gets a little bit tricky, right? Because what we need to do is go to table 2 and find the ampacity based off of the lowest termination temperature, right? 4006 subrule 1 still trumps in this case. 51 amps compared to a number 4's ampacity is 85 amps. Okay, so 85 amps, we go 51 divided by 85 lands us perfectly at 0.6. Right, so when we go to note 3, table D3, again at the 90-degree column, because specifically we're using that 90-degree insulation when we use note 3. Okay, so if we go 90-degree column and we go all the way across to the 60%, luckily it lands right on the 60%, so we don't have to go up to the next percentage. That gives us 1.04 as my distance correction factor. So we're going to take this number and see, we know that it's 9.9, but multiplied by that distance correction factor of 1.04, what it actually works out to is 10.296 meters. So what we've just determined is this 10.296 meters comes from the number 4 with the distance correction factor applied. That distance correction factor, again, what it's saying is based off of these factors in this question, we can kind of get a little bit more distance than what we're allowed on table D3. And because this number ends up larger than this number that we calculated previously, in this question, I can actually go with a number 4 as my conductor now based on all of these external factors. Hopefully this has helped you guys have a further understanding of voltage drop. If you do have questions, please fire them into the comment section down below and I'll try to answer them as quickly as I can. Thanks for joining me. We'll see you next time.